Okay, this video is going to go over 3 sample problems from these kinematics equations, kind of how to go through them, and then putting kind of the finishing touches on all the acceleration, velocity, and position graphs. Okay, so we've got these 4 math equations here. Okay, they all come from information given to you in the previous videos, but I didn't go over any practice math problems, but I want to do a couple here. So the first one is, an airplane accelerates down a runway at 3.2 meters per second squared for 32.8 seconds until it finally lifts off the ground. And we want to figure out how long it traveled before it took off. So what we know is it starts from rest. Okay, and it accelerates at 3.2 meters per second squared for 32.8 seconds. It's given us up here. Now we want to figure out the distance. Okay, so we have acceleration, we have time, we have an initial velocity. We want to solve for d. Okay, so this is the equation we'd use because we have a VI, which is 0. We have a time, we have an acceleration, and we have our time. So we put the numbers into the equation and solve for d. Okay, there'll be questions similar to this on practice problems and on your test. Okay, now the next question is, car starts from rest and accelerates over a time of 5.21 seconds for a distance of 110 meters. And this time we want to figure out the acceleration. Okay, so we know we've got 110 meters, that's d. We got our time, 5.21 seconds, that's t. And it says it starts from rest, so our VI is 0. So we want to solve for a. So if you look at the kinematics equations you have, the only one that we can use is really this one. Because we have an initial velocity, we have a d, we have a t, we need to solve for a now. Okay, so we have our d, 110 meters. We have our initial speed, 0 meters per second. We have our time, 5.21 seconds. Plus then we have the 1/2. A we don't know. T is 5.21 seconds, and we have to square that. So this whole thing goes to 0. 1/2 times 5.21 squared is 13.57 seconds squared. So you divide 110 by 13.57, and you get 8.1 meters per second squared. Okay, look at what we have, what we need. Use that to figure out what equation we're going to use, and then solve for a. Okay, the third practice problem. A little bit more complex. Okay, accelerates to a speed of 112 meters per second over a distance of 398 meters. Determine the acceleration of the dragster. So we're still looking for acceleration now. We know our initial speed, we know our final speed, and we know our distance. So we don't know a time. We can't solve for anything using time because we don't have it. All right, so V final squared is V initial squared plus 2AD. Because we have V final, we have V initial, we have D, we got to solve for A. So V final, 112 meters per second, we got to square that. V initial starts from rest, 0. 2, A we don't know, we know D is 398 meters. So when you square 112, you get 12,554 meters squared per second squared. 0 squared is 0. 2 times 398 is 796 meters. Okay. So your velocity final squared divided by your 2 times your distance is going to get you your acceleration of 15.8 meters per second squared. Okay, like I said, there will be sample problems to work on for these as well. Okay, so jumping to graphs. A little refresher on your graphs. If you have a position versus time graph, the slope of that is your velocity. Okay. When you make a velocity versus time graph, the area under the velocity versus time graph is your displacement. Either you can find that by taking if it's a rectangle base times height, if it's a right triangle 1/2 base times height. The slope of that velocity versus time graph is your acceleration. And the area under your acceleration versus time graph is how much you actually change your velocity over time. Okay, so we have these graphs. Start off with this position versus time graph, and if you notice, starts kind of shallow and gets steep. Okay. Now, if we take this same graph, this same data, and figure out the slopes of all the points, it looks like this, where you get a constant velocity graph. So when you a constant increasing velocity graph. Okay. If you notice, it's getting steeper, which is what this velocity, the position versus time graph is steeper, which is what the velocity versus time graph does as well. Okay. And because the velocity versus time slope is constant, that means we're going to have a constant acceleration. Okay. So ever getting steeper position versus time means a constant slope velocity, which means a constant acceleration. We're gonna practice on that a little bit in class, and you're gonna need to do more information with that as well. Okay. Kind of a more complex problem. Okay. We have a position versus time. If you can kind of imagine what's going on here, the object starts at the origin, goes up, comes back down to the origin, goes backwards, comes back towards the origin, and keeps going. Okay. So it starts at a certain speed. Then it slows down. Notice this is v. V is 0 at the top of that. Okay. And then right here, the object changes its velocity and starts to slow down a little bit until it gets here, which is where v is 0, because then it stops and turns direction. Okay. And then at v is 0, okay, it stops moving, changes back to changes direction. Okay, and then up here it has a constant speed, which is what we see right here. Now, to go from velocity to acceleration, you just look at the slopes. So this slope is negative, it's going downwards, so we have a negative acceleration. This part, it's a positive acceleration, about the same as it is negative on this first part. So it just jumps up here. This part, we have a constant positive acceleration, so we have here. And this part, we have a flat line, no change in velocity, no acceleration. Let me show you what this looks like in practice. Okay, so we have this little simulation here. We have a person who's at a position of negative 10 meters from the origin. Right now he's not going on velocity and he doesn't have an acceleration. Now, if I give him, let's say a 3 meter per second velocity, he's going to go that way at pretty much a constant speed. Okay. Now, if I was to look at, I'm going to put him back. To negative 10. So we're going to look at some graphs now. Okay, let's start with position versus time. And take away the walls. Okay, so we have negative 10 initial position, velocity of 2 meters per second. And if I show the vector for the velocity, he's going to go that way. Now watch the graph. Okay. So when he gets to 0, here, his velocity is constant. Okay, and notice it's a constant velocity. Okay, and it's positive, and he's going towards the 0. Now, if I was to make that velocity a negative 2, and I play him, watch what happens. He goes back the other way. Okay. So, initial position, positive velocity, he's going away, getting steeper positively. Negative velocity, the position is going to get more negative. Okay. So now if we do that same motion here, we have our velocity of 1. We make them go. If you notice here, we have a position versus time graph getting more positive. Velocity versus time graph remaining constant. Acceleration is 0. Okay. This time I'm going to make an acceleration of 1, velocity of 1, and we start off at our negative 10 position. Watch what happens. Okay, so if we look at what happened here, our position graph is no longer constant. It's getting steeper. At our velocity versus time graph, because our position curves, our velocity slope is constant slope of velocity versus time, which means our acceleration is constant. Okay. Final example here, we're going to start positive. Our velocity is going to be negative, and our acceleration is also going to be negative. Watch what happens. Okay, so our position versus time graph gets steeper but more negative. Velocity versus time graph, the velocity increases because the position time graph is getting steeper. However, the acceleration remains constant. Okay, this is what happens when an object we have them running and speeding up, but if you drop a ball, the position versus time graph gets more negative, steeper. The velocity versus time graph speeds up, but our acceleration is constant at a negative 9.81. Okay, so that's the video for this time. Make sure you fill out the form, the formative assessment, and we will talk to you in class. Have a good day.